What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 5, Review Exercises. Let's do it. So for this one, it says to write this in standard form. And again, some books will call it vertex form, but standard form meaning x minus h squared plus k. So the way we're going to start is we're going to space this constant out like that, and then we're going to complete the square, which means we take half of this b term, which is half of 4, or half of that coefficient, I should say, which is half of negative 4, which is negative 2, and you square that, and that's 4. So I'm going to add 4 here, but I'm also going to add 4 to the other side, or you can subtract 4 on this side. But I think it's a little nicer if you just remember add 4 to both sides because you're doing the same thing. Okay, so that might be a little bit simpler. So now we have 4 plus f of x equals, and then this is a perfect square trinomial. So I'm going to factor this, and this becomes x, what two numbers multiply to positive 4 add to negative 4? That's minus 2, aka x minus 2, or x minus 2 squared. And now you can see it's starting to look like that nice standard form. Last but not least, we're going to isolate f of x by subtracting 4 from both sides, and we get f of x equals x minus 2 squared minus 9. Now we can give the vertex because it's x minus h, that's the x value of the vertex, so the vertex is at 2, and then that value here, this is k, negative 9. So the vertex is at 2 comma negative 9. And now to find the x-intercepts, we're basically figuring out when is this function going to equal 0. And to do that, we're going to literally set it equal to 0 and factor. So then the question is, what two numbers multiply to negative 5 add to negative 4? That's going to be negative 5 and positive 1. So there's it in factored form. And what are the two values of x that are going to zero this out and give us our x-intercepts? It's going to be 5 and negative 1, right? You plug either in, the whole thing's going to zero out. So we got 5 comma 0, negative 1 comma 0. And then last but not least, for the y-intercept, you just plug in 0 for x. So that zeroes out, and we're left with negative 5. So the y-intercept is 0, negative 5, and there you go, boom, done. For this one, we're going to put it in that nice standard form. So we're going to start with f of x equals a times x minus h squared plus k. And the nice thing is h and k are the coordinates of the vertex. So since I know the vertex is at negative 2 comma 3, I can plug and chug. So minus negative 2, that's the h, is actually going to be plus 2. And then that positive 3 is out here for k as is. And the last step is we have to solve for a. So that's why they gave us the second coordinate. So I'm going to plug 6 in for the function value and x3 in for the x value. So then I get 3 plus 2, which is 5. 5 squared is 25. Then I'm going to subtract 3 from both sides, and I get 3 equals 25a. Last but not least, divide by 25 like so. And then I get my nice a value. Then I can just rewrite what I had up here, just replacing that a. So I have f of x equals 3 over 25 times x plus 2 squared plus 3. So there's your nice standard form. Boom, done. We're starting with a rectangular plot of land to be enclosed by fencing, and then it says one side is along a river. So we're going to draw out a little river, and then we got boom, boom, and boom. So here's our fence. And by the way, since it's rectangular, these two sides are going to be x and x. And then the other side, we can say y if we want. But since it says the total amount of fencing is 600, if this side is x and this side is x, this side is that 600 total minus whatever those two values are, aka minus 2x. Now we get everything in terms of one variable. It's going to be much easier to solve. So then it says find the dimensions to have the maximum area. Well, what is the area of this rectangular plot? Well, it's length, which is x, times width, which is 600 minus 2x. And then we're trying to maximize this value. So let's simplify this a little bit. We're going to distribute the x, and then I'm going to put that leading coefficient, leading term first with the highest degree, negative 2x squared plus 600x. And we're trying to find the dimensions to maximize the area. Well, here's the thing. This is a parabola, and it's going to look like this. So the maximum is going to occur at the vertex. So in this form here, okay, we can get the vertex by finding negative b over 2a, because the x value of the vertex occurs at negative b over 2a, where this is a, this is b, and c is 0. There is no c term here, so it's 0. So negative b is negative 600 over 2a. 2 times negative 2 is negative 4. And then you simplify that, that's 150. So this means that x is 150, and this is in meters, right? 600 meters, yep. So this is in meters. And then the other side is 600 minus 2 times 150, which is 300 meters. So the dimensions are 150 meters by 300 meters. Done. So the first question is this a polynomial function? And I would say absolutely. It meets all the criteria of a polynomial function. It's got all of these nice positive integer values for exponents. And so once we can come to that conclusion, we can identify the type of polynomial, which is, it looks like a fifth degree polynomial with a leading coefficient of 4, because 4 is the coefficient that is paired with that highest degree term, which gives it that fifth degree. So leading coefficient is going to be 4, and there you go, done. For number 9, this is indeed a polynomial, because once we distribute it, it's going to have a nice polynomial form. So we're going to have, I'm going to put 3x squared at the end, because that's going to end up being the lowest degree. Then we have x squared times negative 6x. That's going to be the middle one, negative 6x cubed, right? Because x times x squared is x cubed. And then we have the x squared times x squared. That's x to the fourth. I'm going to put that in the front. And the reason why is because that is the leading term. It's got the highest degree. So yes, this is indeed a polynomial. It fits all the criteria for a polynomial. And then I would say that the degree is 4, because that's fourth degree. And then the leading coefficient is that invisible number in front of x to the fourth, which is 1. So there you go, done. For this one, we're talking about the end behavior, which can be determined from the degree and the leading coefficient. So the degree is 3, which means it's odd. And the leading coefficient, while it's 4, the most important thing for end behavior is the fact that it's positive. So when you have a positive leading coefficient and an odd degree, whether it's 3, 5, 7, it means it's going to kind of start low, and then whatever happens inside, it's going to end high. So that's kind of a common thing that we can tell with a polynomial. I don't even need to look at these. And you can verify that because think about it. As you plug in really, really big x's, imagine plugging in 10, 100, 1,000. These are going to not be so relevant because they're way smaller in terms of degree. So then you imagine, 1,000 cubed, that's like 1 billion times 4 is 4 billion. That sure looks like it's approaching positive infinity. Likewise, when you plug in negative 1,000, that's going to be negative 1 billion when you cube it times 4, negative 4 billion. So definitely looks like, as we go to the left, approaching negative infinity. So now to put it in formal terms, as x approaches negative infinity, as we mentioned, the function is approaching also negative infinity. It's going down. And then as x approaches positive infinity, the function value is going up, aka approaching positive infinity. Done. So here we're meant to find the zeros of the polynomial, and the nice thing is everything is already factored. So the first thing is what's going to send this binomial to 0. That's going to be negative 3. And then it says, what are the multiplicities? Well, that's determined by this exponent around that binomial. So this is an exponent of 2. We have a multiplicity also of 2. What about this one? What's going to zero this out? That's going to be positive 1/2, right? 1/2 times 2 is 1 minus 1 is 0. That doesn't have an exponent, or it does, but it's 1, right? So this is just a simple multiplicity of 1. Last but not least, what's going to zero this out? That's going to be negative 1 with a nice multiplicity, aka exponent of 3. That's how you do it. Done. For this one, in order to find the zeros, we're going to have to factor it. And since it's 4 terms, you're probably talking about factoring by grouping. So I'm going to show you how that works. We're going to pair these up and pair these up and see if there's a GCF. So for the first two, x squared is the GCF, so I'm going to factor that out, and we got a nice x minus 4 left inside. And I know that's correct because if I redistribute it, I get x cubed minus 4x squared. So we know we've done that correctly. And now this part, there's nothing to factor out, but that's actually cool because look, now I have x minus 4 occurring in 2 places, and that means we've done factoring by grouping correctly. But I could theoretically pull a 1 out, right? Because I want to pull something out and have it in front of the parentheses. And the reason why is because now when we get to this point, these guys kind of come out together in their own binomial, and then this is yanked out of both of them, that x minus 4, hence we get something that looks like this. So now this is in factored form. And if we're trying to find real zeros, there's nothing real that's going to send this to 0. You could have maybe I squared is negative 1, but that's not a real 0. So for this one, though, we do have a real 0. What's going to zero that out? That's going to be 4 with a multiplicity of the same number as the exponent in invisible 1 there. So multiplicity of 1, that's how you do it. Done. So for this one, we're trying to find the zeros based on the graph. So we're looking at this graph, and the zeros, again, are my x-intercepts. And it doesn't say exactly what this is, so we're going to kind of estimate. This sure looks like it's crossing through at positive 1/2. And what's the multiplicity? Well, it's going straight down through it. There doesn't seem to be any bounce or any other kind of flattening out. So I'm going to give this a multiplicity of 1. And then we also have it crossing here. That sure looks like right in the middle of 2 and 4. So I'm going to estimate that to be 3. And because it flattens out like this, right, it is going to be an odd multiplicity, but that's probably greater than 1 multiplicity. So we're just going to go with an estimate of a multiplicity of 3. Maybe it's 5, maybe it's 7, but I think 3 is a reasonable guess. So here we go, done. For this one, we're meant to use long division to find the quotient and the remainder, so let's set it up. So again, the denominator is the divisor, and this is the dividend. So now as we divide, we're only looking at these leading terms here. So how many times does x go into x cubed? It goes in x squared times, because x squared times x is x cubed. That's what we want to line up. But we also must multiply against that -2. That gives us -2x squared. As we subtract, I like to say negate, negate, and then we add them together. A little bit easier for me to comprehend, so that's why I recommend it. Cancels out, -2x squared plus 2x squared, those cancel out. And then we're going to drop that 4x down here. Now, normally we drop one term at a time and then go again, but we may as well drop both because we already can see that we still have a variable and a constant, so that's okay. And then what times x is going to give me that 4x? That's going to be +4, because 4 times x gives us that nice 4x, and then 4 times -2 is -8. Once again, we're going to negate, negate, and then add together. Cancels out. 4 plus 8 is 12. So we have a quotient of x squared plus 4 with this bottom part as the remainder of 12, and that's how you do it. Boom, done. So for this one, we're going to set it up in long division. The top is the dividend that goes on the inside. The bottom is the divisor that goes on the outside. Now let's begin. So we're looking at the leading terms only, and we say what times x, or how many times does x go into x cubed? X squared times, right? Because x squared times x gives me that nice x cubed. And we also must multiply against the 3, which gives us 3x squared. Now we're going to subtract, but what I like to do is distribute a negative. So I say negate, negate, and then we add together. Those cancel. -2x squared plus -3x squared is -5x squared. Bring down that 5x. And then we say, how many times does x go into -5x squared? It goes in -5x times, because -5x times x is exactly -5x squared. And then that times the 3 gives me a -15x. Again, we're going to negate, negate, add these together. They cancel out. Add those together. We get a nice 20x, drop the -1. Last but not least, what times x gives me 20x? That's going to be 20. So 20 times x is 20x plus 20 times 3, which is 60. And then we subtract, aka negate, negate. Those add together, cancel out. -60 and -1 is -61. So now we have up here, we have our nice quotient. And over here, -61, we have the remainder. And so now if we're going to write it in our final format, by the way, it's going to be x squared minus 5x plus 20. That's our quotient. And then we bring that remainder in like this, that -61, but we drop it on top of the divisor. So this is what we get for our final quotient. Done. For this one, we're going to start off by putting this in our long division form. So the numerator, aka is the dividend, which goes inside the house, and the denominator, aka the divisor, goes out here. And then let's go looking at only the leading terms. So how many times does x go into 2x cubed? It goes in 2x squared times. We multiply. Now we get 2x cubed plus 2x squared times 4 is 8x squared. Then we negate, negate. These guys cancel out when you add them together. 6x squared plus -8x squared is -2x squared. Drop that -11x like so. X goes into -2x squared, -2x times, because -2x times x is -2x squared. -2x times 4 is -8x. Again, we're going to negate, negate, right? Multiply by -1, then add together. These cancel out. -11x plus 8x is -3x. Last but not least, we'll drop the -12. X goes into -3x, -3 times. So -3 times x plus 4 is -3x. -3 times 4 is -12. Look at that. We negate, negate. These cancel out. -12 plus 12 is 0. So that's my remainder. This is my quotient. And now if we're going to write this in our final format, normally we'd say this, 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 and then plus the remainder. But here it's a perfect factor because we got a remainder of 0. So they want us to write this in factored form. So we divided by x plus 4. So I can literally say x plus 4 factored out with that remaining quotient on the inside, 2x squared minus 2x minus 3. And that's how you do it. Boom, done. So for this one, we're going to start with the rational zeros theorem, which tells us that if there are any rational zeros, it's going to come by taking all the factors of this last term divided by all the factors of this first term. So the factors of 8 are 1, 2, 4, and 8. By the way, that's negative, but it doesn't matter because these are going to be plus minus regardless. And then when the factors of 2 are going to be plus or minus 1, plus or minus 2, which means all of our possible factors are all of these divided by 1, which is just 1, 2, 4, 8, as well as all of these divided by 2, which also include 1/2, 2 over 2, but that's still 1, 4 over 2, which is still 2, and 8 over 2, which is still 4. So we have these 5, but really 10 options because of the plus or minus. Now what we do is we'd start running through these possibilities in synthetic division, and everything where you get a remainder means it's not a factor. So we're going to run through, let's say we'd start with 1, then -1, maybe then 2, then -2. So I'm going to jump ahead to -2. I do know that -2 works, but this is what you're going to see when you plug in something that gives you a correct output. So here we're going to take these coefficients in descending order of degree. So we got the 2x cubed, -3x squared, -18, and -8. And as we run synthetic division, we drop the 2 down and then multiply by that number in the box. So 2 times -2 is -4. Add -7. -7 times -2 is 14. Add to -18, we get -4 times -2 is +8. And look at that. We get that beautiful remainder of 0, which means x minus -2, aka x plus 2, is indeed a factor, which also means that -2 is one of our zeros, aka solutions to this. Now, we have, when you factor out that x plus 2, what are you left with? You're left with 2x squared minus 7x minus 4. How did I know this paired with x squared? Because that first term, that first coefficient pairs with 1 degree less than what we started with. So now I can keep running synthetic division, or the better idea is once I get to a nice quadratic here is I can factor. So I'm going to factor using the star method because of that leading coefficient, with a going up here and here, a times c, -8 going up top, and then my b term, -7, going down here. Asking the question, what two numbers multiply to this and add to this? And that would be -8 and +1. Then I'm going to reduce this side like a fraction. This side can't be reduced, so it's good to go. This side can be divided by 2, so then I got 1 over -4. And now this is how this factors. It becomes 1x minus 4. Top number goes with the variable. Bottom is the standalone constant. This becomes 2x plus 1. And so now I can see the zeros. Now I can see the other solutions. It's going to be when this zeroes out, which is at 4, and when this zeroes out, which is at -1/2. And we already know that we have -2 as a solution as well. So here are your 3 solutions done. So for this one, we're going to start with the rational zeros theorem, thinking of every factor of 12, which is 1, 2, 3, 4, 6, and 12, all plus or minus. And then all the factors of the leading term, which are just 1 and 2. And then every ratio of these over every possible option of these mixed around, that gives us all your possible rational roots. So obviously everything divided by 1 is just itself, and then everything divided by 2, we'd also have to add in 1/2. I'm not going to add in 2 over 2 because that's still 1, and we've got that covered. Then we got 3 over 2. We also have 4 over 2, but that's covered by the 2. We have 6 over 2, that's covered by the 3, and 12 over 2, that's covered by the 6. So these are the options in here. So what you're going to do is you're going to kind of run through these options in synthetic division with this polynomial to find the zeros, aka the solutions, because it's set equal to 0. So normally I like to start with 1, and I'm actually going to start with 1 here. I'm just letting you know I'm doing it with the knowledge that I know it's going to work, but usually if you don't know it's going to work on a test situation or in the homework, you're going to have to keep running through these options until you get a hit, meaning until you run synthetic division with a remainder of 0. That tells you you've got a solution. So let's start with 1, and we got the coefficients in descending order. 2, -17, 46, -43. Don't forget those signs, right? That minus really makes that negative. And then +12. Now let's run synthetic division. We drop the 2, boom. 2 times 1 is 2, plus -17, -15 times 1. -15 plus 46 is 31, times 1 is 31, plus -43 is -12. -12 times 1 is -12, plus 12 is 0, that nice remainder of 0. So we know that 1 is a solution. Now, because we don't have a quadratic yet, we can't just say, hey, let's write it out and factor. So we're going to run it again. Next, I might try -1, then maybe 2, then maybe -2, and then I'd get to 3. So you're going to try these values out, and if they're not going to work because you're going to get a remainder that's not 0. So that's how you know you got to keep going. So then maybe we're going to get to 3, and let's run it with 3. And we're only going up to this. We don't have to worry about that 0 now. So we drop the 2. 2 times 3 is 6. 6 plus -15 is -9. -9 times 3 is -27. Plus 31 is +4. Times 3 is +12, plus -12 is 0. Again, 3 is a verified solution, right? It does zero this out. So now you got 1 and 3, and now we got it down to 3 terms. Now I can write this out as 2x squared minus 9x plus 4. Again, we started with 4th degree. We've run synthetic twice, so now we're down to a 2nd degree. So now that we have this nice quadratic, we're going to factor, and we're going to do so using the star method, and that's because we got a leading coefficient. So since we have a going here and here, that's 2 and 2. A times C, 2 times 4 is 8 going up top. And then that B term, -9, goes down here. So what two numbers multiply to +8 add to -9? That'd be -1 and -8. This is good to go because it can't be reduced. But this, like a fraction, can be reduced. Divide by 2, and you get 1 over -4. And now that in factored form would be the top number goes with the variable. So 2x minus 1. And then this would be 1x minus 4. So what's going to zero this one out? That's going to be +1/2. What's going to zero this one out? That's going to be 4. And then we also already have our two other solutions with 1 and 3. So there are your 4 solutions done. Here we're going to use Descartes' rule of signs to find the total number of positive and negative solutions. So to find the total number of positive solutions, if they do indeed exist, we look at the sign changes as is. So we're going from positive to negative, that's 1, and then negative back to positive, so that's 2. So we have potentially 2 possible positive solutions, but we could also have 0 because we can also go down in increments of 2. So we could have 2 or none. Those are my possibilities for positive real solutions. And then for negative, we plug in -x for x in every instance, so that becomes -x cubed. -x squared is still the same. It's still +x squared, so that doesn't change. Negative here makes that +2x, and then 4 is still positive. So now in this version, we have negative, positive, one sign change that stays as positive. So we have one possible negative real solution. So these are your answers. Done. For this one, we're going to start with the vertical asymptotes, which are at the places where x is going to zero out the denominator, and it's going to zero it out at x equals 5. So that's your vertical asymptote. Horizontal asymptote, since the degrees on the top are the same, it's found from the ratio of the coefficients of the leading terms, which is 1 over 1, and that's y equals 1. And then to find the intercepts. Now, first, let's find the x-intercept. That's when it's going to zero out the numerator, and that's going to be when x equals -2. And then the y-intercept is literally when x equals 0. So the nice thing is we just plug in 0, we get 2 over -5, aka -2/5. So now what we're going to do is we're going to start plotting these out. So I see a vertical asymptote at x equals 5. That's a vertical line here. And then we also have a horizontal asymptote at y equals 1. Then we got a couple other points. We got an x-intercept at -2. We also have a y-intercept at 0, -2/5, which is somewhere right here. So this gives us a really good idea that the function to the left is going to be like this, because we're just going to come and bring it to hug the asymptote as we go left and as we go to the right, approaching this. But this is a hard barrier, this vertical asymptote. Now, the likelihood is that the other part of the function is going to be up here, but we're going to double check. We're going to plug in something a little bit greater than 5, a little bit to the right of that, which is 6. So we plug in 6, we get 6 plus 2, which is 8, over 6 minus 5, which is 1. So we see that at 6, we have a point of 8. And that's probably good enough. You could plot a couple more points if you want, but this is good enough to say that it's likely going to look like this. So there's our graph. Done. So this one, we're going to start by factoring both the numerator and the denominator. So here I can pull out a 3, and then I've got x squared minus 9. And that denominator is a nice trinomial that we can factor into two binomials. And the way we do it is what two numbers multiply to -2, add to +1. That's +2 and -1. And then this is a difference of squares on top that can be factored further to x minus 3. x plus 3. And just to verify, you see if you FOIL it, you get x squared, 3x, negative 3x, those cancel out. And then negative 3 times 3 is negative 9. So that's how you know it's factored correctly. And then we have this x plus 2, x minus 1 still on the bottom. So now let's start with the vertical asymptotes. I have two places where the denominator zeroes out. That's at x equals negative 2 and x equals 1. So there's my vertical asymptotes. What about my horizontal asymptote? Well, I'm looking at the degrees, and the degrees are the same top and bottom. So I take the ratio of those coefficients and set that equal to y, which is 3 over 1, which is just 3. Now, when we talk about the x-intercepts, we're looking for what zeroes out the numerator in this nice factored form. That's going to be positive 3 and also negative 3. So those are my two x-intercepts. And then my y-intercept is when I plug 0 in for x and I solve for y. So 0 in here. And I'm going to the non-factor form just because it's faster. So then I get negative 27, right, over 0 plus negative 2, which is negative 2. So that the negatives cancel out and you get 0, 27 over 2, which is about 13.5. So now we got a lot of good information. Let's start with the vertical asymptotes. So we got x equals negative 2. So that's a vertical line lined up literally with x equals negative 2 and as well as x equals 1. And then we got this nice horizontal asymptote at y equals 3. And then let's plot these other points. We got 3, 0, which is occurring here. We got negative 3, 0, which is occurring here. And then we got a y-intercept of 0, and that's 13.5 is 27 over 2. So somewhere up here. So now on the right side, we got enough information to kind of say, hey, I've got that 1 point. I got that nice x-intercept. So then we're just going to hug the asymptotes. Now, one thing you might want to check for is to see if we are indeed crossing the horizontal asymptote. Sometimes that happens. It might cross up and then still come back down and still hug that line. But that's something you want to check for. Now, this one doesn't, but the way you'd verify it is you'd set this equal to the horizontal asymptote, which is 3, and see if you get any values for x. But again, most of the time it won't, so we're good here. We don't have to worry about it, but it is something to check for in the future on an assessment. So again, this one here is going to hug the asymptote as well right there at the vertical. It'll never cross the vertical, but it could cross a horizontal occasionally. Now we come to this middle part. I see I have a point up here, and so it could do a couple of things. It could go up, and then it could go up here. It could also come down. Maybe it crosses that asymptote as we mentioned. Now, like I said, I'm telling you it doesn't, but if we want to check just to be certain that it goes up and up like this, we want to plug in some other values. So for example, if I plug in a half here, a half squared is a fourth times 3 is 3/4 minus 27 is negative 26.25 over, plugging in a half here is a fourth plus a half is 3/4 minus 2 is negative 1.25. And as we do the division, you don't have to get so exact, but we can tell we're going to get something bigger than 13.5. So we know we're going above here. So it sure looks like we're going to be going up as we go to the right. What about to the left? Let's plug in a negative 1, and we can do that quickly. That's 3 times negative 1 squared is 3 minus 27 is negative 24 over negative 1 squared is 1 plus negative 1 is 0 over negative 2. And that's going to give us a value of 12. So it is going to drop down here to this point. So far it looks like it's going down. So maybe it does go that way. But let's plug in one other value just to be safe. Let's plug in negative 1.5, just a little bit closer to this asymptote. And when you plug it into a calculator, you actually get 19.8. So it looks like it's shooting back up. It's coming up here. So we can say that it's going to go back up like this. And by the way, if you do check it by setting this equal to that horizontal asymptote and be like, oh, it never crosses, then there's no real doubt that it will have to go up like that. But you can figure it out this way too by a little trial and error. So there's your answer. Done. So for this one, we're meant to find the slant asymptote. And first of all, the way we know that there's a slant asymptote is because the degree on top is bigger than on bottom. So now to find it, we set up a long division problem like so, top divided by bottom, and we take it from there. X goes into x squared. X times x is x squared. X times 2 is 2x. And then we negate. These cancel out. And then negative 1 minus 2x, well, those are not like terms, so it's just going to be negative 2x, and then that minus 1 is just going to drop down. Like that's what it is. Or I could have said negative 1 minus 2x. The order doesn't matter, but I did it this way to line up with the x and the constant here. So now what times x is negative 2x? That's negative 2. Negative 2 times x is negative 2x. Negative 2 times 2 is negative 4. And then we negate. add them together, cancel out. Negative 1 plus 4 is 3. So that's the remainder, but the remainder doesn't matter because the slant asymptote is just that quotient at the top, y equals x minus 2, boom, done. For this one, we're trying to find the inverse function with this given domain restriction, and coincidentally, that is right at the vertex, right? Our vertex is at 2, 0. So if this is a function going up, we're talking about taking the domain from this side over, right? So we're ignoring this piece. And that's really nice because when we do get the inverse and it's a radical, we don't have to worry about taking the negative side of the radical, aka that plus or minus. We can just take that positive. So the first step here is I'm going to replace f of x with y. Then I'm going to swap the x's and the y's. And then we're going to isolate. I'm going to start by taking the square root of both sides. So I get y minus 2 equals plus or minus rad x. But as I mentioned, we're only taking the positive side. So we just got radical x. And then we're going to add 2 to both sides. So radical x plus 2. And now if we want to put it in that nice function format, the inverse of f of x, or f inverse of x, is equal to rad x plus 2. Boom, done. For this one, once again, we're starting with this condition that the domain is x is greater than or equal to negative 3. Coincidentally, that is the vertex of this. You can see it's negative b over 2a is negative 3. So what we're looking at is we're looking at a parabola where the vertex is at negative 3, and we're taking everything to the right, meaning this portion here. And that's nice because when we take the inverse, we're going to get the radical function going like this, and we don't have to take that plus or minus, right, and include that bottom side. We only have to deal with the positive element of that radical function. So now let's get into the weeds here. We're going to start by replacing f of x with y. Then we're going to swap the x's and the y's. And now our goal is to isolate. But when we have the situation of a y squared and a y, we're going to have to do something called completing the square. And that's to help us isolate y. So we're going to take half of this, which is 3, and square it, which is 9. And then we're going to add it to both sides. So that's why I left a little bit of room there to squeeze that in. So now this is a perfectly factorable trinomial. And it's y plus 3 times y plus 3, aka y plus 3 squared, equals 9 plus x. But now I'm going to add the 2 to the other side and make it 11 plus x. And that's cool because I need to isolate this anyways, right? I need to isolate y. I'm going to take the square root of both sides. Normally it'd be a plus minus, but because we said we already restricted the domain and we're only taking the positive side of that radical, we just leave it as radical 11 plus x. And then we also have the y plus 3 on the other side. I just switched the sides. It doesn't matter. You can put the y plus 3 on the right side as well, but I like it better like this. Last but not least, we're going to subtract 3, right? So square root of 11 plus x minus 3. And now for the final, we give it in this nice function notation. So the inverse of f, or f inverse of x, is radical 11 plus x. And then outside of the radical is that minus 3. There's your answer. Boom, done. So for this one, we're going to start by replacing f of x with y, and then we have 4x plus 5 minus 3, and then we're going to swap the x's and the y's. So we got x equals radical 4y plus 5 minus 3, and then we're going to isolate y. So first we're going to add 3 to both sides, and then we get radical 4y plus 5. Then we need to square both sides to get rid of that radical. So now I have x plus 3 squared equals 4y plus 5, right? That just kills the radical. Then we're going to subtract 5 from both sides. X plus 3 squared minus 5 equals 4y. Last but not least, we're going to divide both sides by 4. So I get x plus 3 squared minus 5 all over 4. Now to put it in that nice function notation, we got f inverse of x equals x plus 3 squared minus 5 over 4. But then we have to impose a domain restriction because this is a radical function that just looks like this. This is a quadratic that looks like this, right? So we're going to have to cut one of these sides off. So the question is, like, how do we impose that domain restriction? Well, this actually has a range, okay? This radical function is going to start when this thing zeroes out at negative 5/4, and then you're going to have a y value of negative 3. That's the lowest this is going to go because you're not going to get any lower than 0. This can't be a negative because then it would be beyond a real number, right? Taking the square root of a negative. So this is the lowest point. So that means the range is everything above negative 3. But the cool thing is for the inverse, if I know the range, that ends up being the domain of the inverse, which means the domain is now x is greater than or equal to negative 3. So Here's your final answer. Done. So for this one, it says y varies directly as the square of k. So when it says direct, it's the constant times whatever it gives here, which is the square of x, or x squared. Then it says when x equals 3, y equals 36, which means this allows us to find k, and that's what we need to solve. So 3 squared is 9. To solve for k, we're going to divide both sides by 9, and we get k equals 36 divided by 9, which is 4. So now I can rewrite my equation as 4, subbing in 4 for k, x squared. And then we can find y when x equals 4. So I'm going to plug it into this final equation. So I got y equals 4 times 4 squared. 4 squared is 16 times 4 is 64. So y equals 64. Boom. Done. For this one, it says y varies jointly as the cube of x and as z. So jointly, again, it's like that direct variation, k, the constant times the cube of x and z. So now we got our equation. So now we need to solve for k, and it says when x is 1, z is 2, and y is 6. So we're going to plug and chug. 6 equals k times, and x is 1. 1 cubed is just 1. We don't even need to write that. And then 2 is just 2. So when we divide both by 2, right, plugging in 2 for z, we get k equals 3. So now I can rewrite this as y equals 3 times x cubed z. And then we're going to solve for y when x equals 2. So we're going to plug that in here. And z equals 3. We're going to plug that in here. So we have y equals 3 times 2 cubed, which is 2 times 2 times 2, which is 8. And then with that 3 at the end. So this is 3 times 8, which is 24, times 3 again, which is 72. Boom, done. So for this one, it says the weight of an object, which we'll call y, above the surface of the earth varies inversely. So that inverse variation, again, means we have some constant over something, with the square of the distance, which we'll call x, from the center of the earth. So we'll call that x squared. If a person weighs 150 pounds, that's the weight, that's y, on the surface of the earth, 3,960 miles from the center. That's my x value. That's the distance. So that's k over, and I'm just plugging this in. I'm going to explain why in a second. 3,960 squared. So I'm plugging and chugging. And why do we start with this? Because for direct variation, the first thing, or inverse variation, or any of these variations, the first thing is I need to figure out what this constant is. So this is enough information for me to do so, because I can multiply both sides by 3,960 squared, and multiply by 150 using a calculator that gets 235,224 with 4 zeros, so a huge number. And it looks like 2,352,240,000. Okay, so there's our k. Now we can rewrite this over x squared. And then now we're trying to find the weight, aka y, when the person is 20 miles above the surface. And they said the surface is 3,960. So 20 miles above would be 3,980. So here's what we have. Now let's plug it into Desmos and let's see what we get. And when we plug it all in and round to the nearest tenth, we'll get 148.5 pounds. So y equals 148.5. The units are pounds. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.